Hey, so we are in 124 office hours. We got some questions about 1.1. We're going through 2, 8, 10, 11, 12, 13, 15, and 17. I just got to see what those problems are now. Most of the problems on this homework are about unit conversion and a little bit about significant figures. Number 2 is a little bit confusing because it's asking us to combine multiple conversions, right? So it gives us 2.5 kilograms per microliter, 2.5 kilograms per microliter, and it wants us to get it into grams per milliliter. Make sure I'm not wrong about that. Yep, grams per milliliter. This is a typical unit we use. That's what we use for like density and things like that. So there's a couple different ways we can approach this. I find it most confusing to try and convert everything at once with our typical unit conversion mentality. So I actually split it into top half and bottom half, and that makes it easier. So I do 2.5 kilograms, and I use multiply by 1 trick, so I know 1,000 grams. Oh, except for I should write 4 zeros for 1,000, 3 zeros for 1,000, 1,000 grams per 1 kilogram. That'll get us, there's a couple different ways we could write it. I want to start doing things in scientific notation. This will get us 2,500 grams. The other kind of fun, tricky way we could do this is kilo means 10 to the third. So I can just take this thing and I can say 2.5 times 10 to the third grams. And that's the way that I start to do it. Once I get a lot of practice with doing the unit analysis, that's how I start to do it. And then we go ahead and we do the bottom part, which is microliters to milliliters. Now, here's where I get a little messed up. I think it's a factor of 1,000, but I'm always worried I'm going to mess it up. So I actually convert microliters to liters and then liters to milliliters, even though we'll see it's a little bit silly. So 1 liter has 1,000, 1 million microliters. 1, 2, 3, 4, 5, again. 6, 3, 4, 5, 6 zeros. And again, scientific notation is a little bit easier. We'll look at that in just a moment. And then 1,000 milliliters per liter. Yeah, it is. It is just a factor of 1,000. So you can see a bunch of the zeros are going to cancel out. And we'll end up with 1 times 10 to the minus 3 milliliters. Oh, this is going to be funny, isn't it? This might end up being funny. So you notice we go up by a factor of 1,000 here and down by a factor of 1,000 here. Is this right? Did I mess this up? Oh, no, because it's division. We haven't done the division yet. So we end up off by a factor of 1 million. So now I put these two things together. So I do 2,500 grams divided by 1 times 10 to the minus 3 milliliters. The minus 3 would be coming up top. I can rewrite this as 2.5 times 10 to the positive 3. And if I'm doing this math in my head correctly, I'm going to get 2.5 times 10 to the 6 on top. That doesn't feel right. I feel like I did something wrong.
Right.
And I'm recording it. Can you do me a favor? Punch that in, see if that's correct.
Yeah.
Because kilograms. No, I think it's just 2.5. I think I messed up someplace.
Oh, wait, times the 1 Yeah, that was right.
Oh, positive 6.
Yeah,
Oh, it is right. Okay. I gotta trust my math sometimes. So we're doing some 124 questions. 124. Great. Okay, everyone's 124 today.
129.
Oh, 129. I was like, yeah, no, you're all good. So these are the 124 questions that we're going through. We just did number 2, and I am recording, so it'll get posted afterwards. So yeah, I gotta trust myself, but I split it into 2 parts. The reason I confused myself was because when I was thinking about this, I was like, kilograms, this number on top should be getting bigger. Microliters to milliliters, that number should be getting smaller. And so I was like, oh, they should balance out. But inverse relationship, right? The number on bottom getting smaller makes the whole thing get bigger. So got to keep that in mind. Show you a couple other little shortcuts, right? So microliter, if this is 1 microliter, when I get practiced with this, I don't do the unit analysis. I see 1 microliter, and I just see 1 times 10 to the minus 6 liters. And I just can do that like real quick. The micro means 10 to the minus 6. And we have to be careful because micro means 10 to the minus 6, so people think micro is the 10 to the minus 6 part, but it means 10 to the minus 6. So when you have 1 liter equal to microliters, that's going to be 1 times 10 to the positive 6 microliters, because the micro means minus 6. So the minus 6 and positive 6 eliminate each other. And then you're just same number. But a lot of people say micro means minus 6, so they make this side minus 6, and that's wrong. Be careful with that. So that's number 2. Number 8, do either of you have questions beyond this, or do these hit your questions?
I was confused on 6 and 7.
Okay, we can throw those in there too.
I was confused on 10, which is up there, and then 12, which is okay. Cool.
Okay, so, and we'll get through a couple of these and we'll hop to a 129 question or two. Let's go ahead and look at 6. Let me see what question that is.
For 6, I just could not figure out the percent error.
Oh, okay.
Like,
So you expect that your total
everything I
balance?
tried didn't work.
Okay, so
Did you forget to turn it back into a percentage? That's what I did.
No, I did that.
Okay, never mind, sorry.
Okay. So we know it's exactly 500 grams.
Yeah.
And what was your average value?
It was 542.
Is it 542?
Exactly.
Okay, so like 542.0.
0,
3 zeros. I think 2 zeros.
Right? Or 3.
Let's go 3 zeros.
Either way.
Right, really accurate balances. The balances we have are pretty accurate. So this is what we have for our average, and then we had to say what's our percent. No, that's not it. Okay. So when we want to look at percent error,
Yeah.
what equation did you use for that?
542 minus 500 over 542.
So it's
Is it the opposite?
no, you're on the right track. I'm trying to think of the best way to write this down. So you're gonna have like your you divided by the wrong thing.
Oh.
You're gonna divide by the 500 because the 500 is the real value. So we're seeing how far away. So essentially, this thing on top, this gives us how far off from the actual we are.
Yeah.
And I'm trying to remember some problem someplace. I think it's. Right, so this gets us how far from the actual value we are off.
Yeah.
No, it's real minus actual. I need to flip that back. Or measured minus actual. Right? So this gets us how far we off, how far off we are.
Yeah.
So you can imagine if we were 5 grams off, we divide by 500, that would be a 1% error. But if you were 5 grams off and you measured divided by 505, you're 1.1% off.
Yeah.
A little bit different. It becomes really dramatic when you're 100 grams off. Right? So if you're 100 grams off, then you're 1/5, you're 20% error.
Yeah.
But if you're 100 grams off and you do 1/6, that's a really different number than 1/5. So that's where dividing by the actual is more important. So that got you that one. Let's see. That was number 6. Number 7. This is one that kind of confuses people because they try to do all of these extra things that aren't necessary. You know, we do a very typical thing of this must be complicated, but it's not. So we know, and there's one thing that kind of makes it easier to deal with, and it's a unit that's not put there. So this is number 7. Use 3.27 times 10 to the, I can't see the number very well.
Negative 13.
-13 nanograms. That's our given, and we want to know, now the thing is, here's the unit that's not given. It's given in the words, but not in the way it's written. It says 1 atom of gold weighs this amount. So we can put this as nanograms per 1 atom. And putting that 1 atom there makes it easier to do the unit analysis and find the number of atoms. And then we want to know, we've got 1.0 grams of gold. So we've got 2 different ways we can go about this. Our units of mass are not matching. We need to get those to match. So we can either convert nanograms to grams, or we can convert grams to nanograms. Either way works. I'm actually going to convert the grams to nanograms because this already has an exponent. I don't feel like messing with it. So I'm going to go ahead and I'm just going to, a nanogram, nano means 10 to the minus 9. So that means I'm going to multiply 1 times 10 to the positive 9 nanograms per 1 gram. Right, because that's negative 9, that's positive 9, that's multiplying by 1. So then this is going to be 1.0 times 10 to the positive 9 grams. Now I have to, sorry, nanograms. That was the whole point of what we just did. So we've got this in nanograms, and again, I could have converted this to grams, and I could have had like an extra minus 9. That'd give me a minus 22 for my mass. It's fine to do it that way. Now I just need to get this to cancel out. I know I want this to be equal to a number of atoms. So I'm going to take my 1 times 10 to the 9 nanograms, and I'm going to divide by 3.27 times 10 to the minus 13 grams per an atom. Now the nanograms. The nanograms will cancel out, and the 1 over the atoms just flips the atoms up to the top. Do you know how 1 over works?
Wait,
So if you have nanograms divided by nanograms per an atom,
yeah.
that's equivalent to nanograms times atom over nanograms. So nanograms is going to cancel out, and we're just going to get a unit of atoms.
Okay.
So at its root, all we're doing is dividing 2 numbers. That's it.
Okay.
We just got to do unit analysis and make sure we're following along with the, keeping our units correct as well.
Yeah.
Number 10.
Just got thrown off by cubic. Wondering if I
Oh yeah, cubic is tricky. Right, that was one of the things we spent some extra time on in class yesterday, because that multi-dimensional aspect can really mess with people. So number 10 says, how many cubic milliliters are there in 1,000 cubic centimeters? Sorry, 100 cubic centimeters. So we have 100 cubic centimeters. And we want to know how many millimeters cubed that is. It's not just a factor of 10, right? And that's the part that really messes with people. So if I had centimeters cubed, those are all centimeters in each dimension. This cube, each side is going to be the cube root of 100. Can't do that in my head. Is that like... .6. Each side's 4.6. Random number, but 4.64158 times cubed is 100. Now, in order to get this to millimeters, I have to take each side and convert each side. So this would be, if this was 4.6, I find it easier to think about with numbers. So I like having the numbers there. Millimeters is a factor of 10 smaller. So if I had 4.6 centimeters, that would be 46 millimeters on each side. So my cube becomes 46 millimeters, 46 millimeters, 46 millimeters, where I've rounded a little bit too much, but you can see it's a factor of 10 3 times. And now I multiply those all together, and that should get me my proper volume. The other way to do it, once we realize there's this dimensionality to it, is we can take 100 centimeters cubed, and I just take my conversion of 10 millimeters per 1 centimeter, and I cube that conversion to get it on 1, 2, 3 dimensions. So I convert it there, I convert it there, I convert it there, and that will take care of it all at once. So it's not just off by a factor of 10, it's off by a factor of 1,000. So you end up with 1 times 10 to the 5th millimeters cubed.
Yep.
Right. I find the visual kind of helps as we're first thinking about it, but once we get good at that, and you'll notice there's a lot of problems where I'm doing extra steps, like the unit conversion with the multiplying out, where we get to a point where like, no, I can just do these steps in my head. But early when we're learning this and getting used to it again, or remembering it because we've done it way in the past, it's nice to do the extra steps. I'm going to do number 11, answer some 129 questions, and then come back to 12 and 13, 15, 17.
When I plugged in the 10, because I kept it, instead of the 4.6, I kept it as the square root of 100 times 10. Like after I converted it to the
Cube root.
cube root? Oh, cube
Yeah,
root.
cube
Oh,
root.
that's what I mentioned. Okay.
Cube root of 100 times 10 cubed.
Which lab file is this?
This is Chem 124 MQ 1.1.
okay.
So at a certain point, the Celsius and Fahrenheit scales cross where the temperature is the same on both scales. What is that temperature? So this is a fun kind of concept question, right? It turns out when we think about temperature, and I barely talked about temperature, but when we think about temperature, right, these different scales have different systems associated with them. This is asking about Celsius and Fahrenheit, and we can think about it this way. Celsius crosses 0, and then at 100, it has some relationship, right? Now, we can relate this to the Fahrenheit scale. So if this is Celsius, we can relate this to the Fahrenheit scale. The Fahrenheit scale, when we're at 0 Celsius, is 32, right? So this point that's where water freezes. This point right, and this is how we get the equation for Celsius to Fahrenheit relating to each other, but we can just look that up. And that equation, ooh, can I get it right? Can I remember? Fahrenheit is equal to, which way do I remember it? Fahrenheit minus 32 times 9/5 is equal to Celsius. There we go. This is just like, I can never remember which way I remember it, if it's Fahrenheit to Celsius or Celsius to Fahrenheit. 5.9 Celsius plus 32. Yeah, this is great. Okay, that's the right one? Great. So now we want to find the point where Fahrenheit and Celsius are the same.
Oh wait, is it 5 over 9 or not? 9 over,
5 over 9.
yeah.
5 over 9, thank you.
Checking
Ha,
notes.
yeah, 5 over 9, thank you. So we want to find the point where Fahrenheit and Celsius are the same value. Why am I blanking on this?
What I did was I made both of the Fahrenheit and Celsius equal to the same variable, and then I just.
Oh, there you go. Yeah, there you go. Right, so I want the Fahrenheit to be some value x, and I want the Celsius to be that same value x. And then I just rearrange. So I'm going to have, if I multiply through, I'm going to have, here I'll do it in blue just to be dramatic. I'm going to have 5x over 9 minus 32 times 5/9 is equal to x. I can go ahead and subtract, Oh, it is a negative value, isn't it? Okay, I was freaking x, I'm like, I'm getting an extra negative. So I'm gonna add the 32 over, subtract the x over, so I'm gonna have 5/9 x minus x is equal to, I'm just gonna get a number, 32 times 5/9. I can rearrange this to be 9/9 x multiplied by 1. And then when I do 5 minus 9, I can just put this as 4/9 x. Multiply 9, divide by 4. You're going to get 5/4 of, oh, I'm sorry, I forgot a negative. Thank you. I saw you were like, Right, so then I can rearrange that and just do the algebra. Was that okay?
Yeah.
Cool. Okay.
Basically asked the same kind of principal question about like the speed of light through something, but 17's got delay.
Did we not do 8?
No, we skipped over 8.
Oh, let's do number 8 and then we'll do 12, 13. 12, and the funny part with all of these, because I think all of chemistry is hilarious. No, I'm kidding. The interesting part, the funny part is, they seem impossible, and then I show you one thing and you're like, wait, that's it? So let's do number 8 and number 17, right? Both of these questions are asking about speed of light and how fast something travels, right? Or like how far it travels. So we're given, and I'm going to do this in the way that I modeled in class the other way. Explicit result. And we've got some implied information. So what are we given explicitly in number 8?
Explicitly, the measuring tool has a path length of 1 centimeter, and light travels at approximately 3.0 times 10 to the 8th meters in a vacuum. Meters per second in a vacuum. How long does it take for light to travel 1 centimeter in nanoseconds?
Trying to find time. So if I've got a velocity that's meters per second and I got a distance that's in centimeters, how do I get to time? How do these three things, the two explicit things, and the result we're trying to get to relate to each other?
I mean,
It's a physics thing.
yeah.
Velocity times time equals distance. Right?
Yeah, that's okay.
Now, the units work out really well because I've got meters per second. If I multiply by seconds, I'm left with just something in meters. So velocity times time equals distance.
Okay.
That's it. We've got velocity. I can change this to d for distance. I didn't want to put d because it could be density, but this is distance, right? The units give us the context of that. So if I plug in the distance of 1 centimeter, the velocity of 3, well, make sure we get our units right. Plug in our velocity, 3.0 times 10 to the 8 meters per second times time equals 0.01 meters traveled. Divide over, that's it. Number 17, exact same thing, except now you want to find the distance for a particular time and a particular velocity.
Got it. So just rearrange the equation.
Just rearrange the equation. Really similar to what we were doing with molarity and density and molecular weight, where there's 3 variables and we just got to rearrange it to the proper one.
Yeah, just needed that physics.
A little bit of physics, right? And we can also get to the physics when we write down our explicit part. I've got a time, a distance, a distance. There's got to be some way that I can rearrange things to get to a time. So a little bit of analysis there. Now 12 and 13.
Is this 127?
No, this is 124, 127.
Got it. Okay.
Yeah.
Are we gonna? Okay. Just let me know when we switch back.
Yeah, we'll let you know.
Okay.
So let's see, we've done that, we did that, we did that, we did that, we did that. Okay, and we just did number 17 as well. So 12 and 13, these are the two that are, in my opinion, the most tricky on the homework. That's part of why I talked about them in class yesterday, and I was kind of surprised, because normally I do this problem in class, because people are like, yeah, this is really confusing, what's going on? And everyone was like, no, it's fine. I was like, okay. So I just talked about it. So I just talked about it for a little bit, and everyone was like, yeah, let's move on. And I was like, oh, okay. So let's go ahead and do it. Because that kind of surprised me, but, you know, a bunch of engineering background, who knows?
Once you give the volume, it kind of clicked for me. But I just needed that extra, like, there's your hint. I was like, oh,
Yeah.
okay, got it.
So the main trick here is, and I find this easier if I have a physical object for consideration, right? We're analyzing a physical object. This is a graduated cylinder, and we want to know the distance between the marks. I'm showing the camera.
I was like, oh, you can see.
Yeah. So we want to find the distance between the marks. Essentially what this means, and the distance between the marks makes some shape. So essentially what I want is I want the volume that I measure to be equal to the volume of some shape. Now, the problem is specifically asking for 1 milliliter measurements. And this is the part where having the physical object helps. What's the shape between 2 marks?
A straight line.
Well, I mean the three-dimensional shape. If I take a cut out of this thing, you make a cylinder. What's the equation for the volume of a cylinder? I r squared times h. In the problem, we are given r, pi is a constant. I just have to make sure my units match and rearrange. It's like, oh, that's it, right? The places to be careful. 1 milliliter is 1 centimeter cubed. The inside is given in a diameter rather than a radius, so make sure you cut it in half. And it's given in millimeters instead of centimeters, so we have to make sure that our units match there. It also is asking for the final answer to be given in millimeters, not centimeters. So in my opinion, it's a little bit easier to switch the volume from centimeters cubed to millimeters cubed. It's going to be a factor of 10, 10, 10, so it's going to be a factor of 1,000. So it's going to be 1,000 millimeters cubed equals pi r squared h divided by the pi r squared. That's it. Now, 13 is a bit trickier. So what I'm going to do for 13 is I'm going to give you the part that most people have trouble with, and then I'll let you work on it for a little bit. So number 13 asks you to, it does this weird thing where it's like, okay, great. Ooh, jeez. It's like, great, okay, so we've got this thing. We got this tube of glass. How much does the tube of glass weigh? It gives you the density of glass. You know, the inner diameter, outer diameter. How much does this tube weigh? I think like 20 grams, estimating. I don't do grams that well, but I'd say 20 to 50 grams. Now, that of course is not going to be the right answer, but that's, you know, it's always nice to have a ballpark of what answer we're expecting. It could be a different graduated cylinder than this, so it could be pretty different from that. Plus my estimation of holding in my hands might be wrong. But if we get something that's on the order of milligrams, we're obviously wrong. If we get something that's on the order of kilograms, we're obviously wrong. It should be on the order of, you know, like less than 100 grams. It should be in the, like, you know, 50 to 50-ish grams range. The big mistake most people make is they take the outer diameter, they use their height that they solved for in that one, and they do height times 100, and they solve for a glass rod, not a glass tube. We have to subtract. So you use the outer diameter to get a glass rod, and then I'll change colors just to be dramatic, and then you get your inner diameter to get your rod of air, right, because there's essentially like a rod of air through the middle. You subtract those two, make sure I don't drop that, and you end up right? That's going to give you your tube. At that point, you can find your volume of glass, multiply by density, that gives you your mass of glass. But the subtraction step of like, everyone forgets how to find the volume of a tube. And a lot of you haven't had a lot of experience with glassware, so you might not have even known how to think about a graduated cylinder, which is why it's way easier to actually have one to think about.
For 12, do we use the inner diameter or the outer diameter for the radius?
Ooh, where do we put the liquid?
The inside.
Inner diameter.
Okay.
So go ahead and try those. We'll see how it goes, and I'll